Welcome back to my YouTube channel. Today we will prove the finite subgroup test step by step. Okay. Statement of the finite subgroup test is say that H is a non-empty finite subset of any group G. Okay. If H is closed under the operation of G, then H is form a group of G, subgroup of G. Okay. So now prove. Okay, here we use two-step subgroup test. Okay, so we only show three conditions. First is H is non-empty, and second is H is closed under operation. Okay, and thirdly we show A inverse belongs to H whenever A belongs to H. Okay, if three conditions hold, then we say H is a subgroup of G by the two-step subgroup test. Okay, now in our hypothesis, here H is non-empty is given, and here also H is closed under operation also given. So here already first condition H is non-empty is given. Okay, and second also given, H is closed under operation is given in hypothesis here and here. Okay, here we need to show A inverse belongs to H whenever A belongs to H, then proof is done. Okay, so now if A is identity, okay, identity inverse is equal to identity. Okay, that is A inverse equal to A. So in this case we are done. Okay, now if a non-identity element, okay, so consider the sequence A square, AQ and so on. Okay, and also given H is closed under operation and operation. So that is, so A belongs to H. Okay, so A dot A also belongs to H because H is closed under operation. Okay, so this A dot A also belongs to H, that is A square belongs to H. Okay, and similarly A dot A square also belongs to H because A belongs to H, A square belongs to H, by the closeness of H is also belongs to H, that is AQ belongs to H, and so on. Okay, so we have all the terms of the sequence A to the power n in H. Okay, now here also given H is finite. Okay, in hypothesis here H is finite subset of G here given. So we must have AI is equal to AJ for some I greater than J. Okay, suppose this is not hold for every I and j. So here the term of the sequence, that is a square and aq and so on, this term all are different. So this implies H is contains infinitely many different elements, because all term of this sequence belongs to H here. Okay, so that means H is contains infinitely different element, but here given in hypothesis H is finite, so which is a contradiction, because finite set only contains finite number of elements. Okay, so this condition must be hold. Okay, so this implies a to the power I minus j is identity. Okay, where I greater than j, and also a not equal to identity. So this implies I minus j greater than 1, strictly greater than 1. Why? Because if I minus j is equal to 1, that is a to the power 1 is equal to identity, this implies a is equal to identity, which is a contradiction, because we already given a is non-identity element. Okay, so this is I minus j always strictly greater than 1. Okay, so now calculate. Now to calculate the value a dot a I minus j minus 1, that is equal to a to the power I minus j, that is equal to identity from here. Okay, so that is a to the power I minus j minus 1 equal to a inverse from here. Okay, and also I minus j minus 1 greater than equal to 1. Okay, since I minus j strictly greater than 1. Okay, so this implies a to the power I minus j minus 1 belongs to H. Why? Because here, from here, all positive integer power of a each belongs to H, already given, already show. Okay, from here already we show. So that is here I is integer and j is integer and 1 is also integer. So I minus j minus 1 also is an integer, and this is also greater than equal to 1 from here. So that means a to the power I minus j minus 1 is member of the sequence, one member of the sequence. So this implies this is must belongs to the H. So that is, this implies A inverse belongs to H, because here a to the power I minus j minus 1 equal to A inverse. Okay, so hence the proof, because A is any arbitrary element which is non-identity. Okay, so first condition are given and second condition also given, and third condition we prove. So by we conclude that H is a subgroup of G by the two-step subgroup test. Okay.